All right.
Welcome back.
All right. So the opposite of that interpolation is when your value falls outside of the data that's given to you. Okay, so like on the example 1, remember your x values were between 6 and 16. So when it falls outside of that data, so it would fall outside of the values of 6 and 16, it's called extrapolation. Extrapolation. Okay. And if you notice, the prefix is extra. So it's extra data that's outside of what was given to you. Okay, so like right here, we got 20 commercials. 20 is beyond the 6 to 16, isn't it?
Yeah.
So that's outside of the data that's given to you, so that's called extrapolation. And when they want you to find something, they call it extrapolate. Okay, so the 20 commercials. All right, so looking back at example 1, is the number of commercials your X or is it your Y?
Wait, what was the question?
Is the number of commercials your X or your Y? It's your X. So here they're asking you to find the output when X is 20. All right, so let's go back to Desmos. And we're going to use our equation from yesterday. Okay. All right, so I'm going to come right here and I'm going to say 0.51x plus 3.71. Now, we can find x equals 22 ways. We can either come right here to the next line and we can say literally x equals 20 and see where they do what? Where they intersect. Okay. Oops, I do have a 2 there, don't I? Let's try it again. All right, so when x is 20, what's the number of sales units? All right, and let's round that to the nearest tenths. So here we get 13.9 sales units. Okay, so again, when they ask you to find a data value that is in between the data that's given to you, it's called interpolation. But when it's outside of the data that's given to you, it's called extrapolation. Now, when you go into the outside world and you actually have to use this for some of your businesses. All right, so as I was saying, in the real world, when you have to create reports and whatnot, and you use this statistical stuff to do those reports, you really don't want to use extrapolation a lot because that's not always going to give you the most accurate answer. And I think yesterday the example I gave you is like if we were analyzing egg production on a chicken farm, and we looked at it for 2 weeks, and we wrote down, the daily egg production. Well, when we create that prediction equation, those prediction equations don't have ceilings. There's no limit. So if we say that, with looking at the next trend, let's say we have 10 chickens, that looking at the trend, our prediction equation, if we use something outside of the data that we have, it might tell us that we can have 700 eggs laid in one day for 10 chickens. Well, are 10 chickens going to lay 700 eggs?
Nope.
No. So sometimes when you extrapolate something, you're not always going to get the correct answer. It's going to give you something that's an outlier, something that really won't exist in the real world. So that's why in the real world, we really don't want to use extrapolation. You always want to use interpolation. All right, so coming right here, looking at example 2. Oh, and it also says it right here, that this can be problematic to extrapolate values because it's not always a certainty that the data beyond what we were given will follow the same pattern as the data that we already have. So what that's saying in our language is that sometimes it's going to give you an answer that's not really going to happen in the real world. All right. So right here in example 2, we got large bags of dry dog food provide daily feeding instructions based on the weight of the dog. The data set shown was developed from a chart provided on one dog food bag. Determine a mathematical model from the data to show the relationship between the weight of a dog and the amount of dog food recommended. All right, so everybody put this into Desmos and find my equation for me. And make sure you notice that for some reason it printed weird. That's supposed to be a 36, a 57. All right, now when you get your equation, you can round it to 2 decimals. So round it to the nearest hundredths. Mm-hmm. All right, so let's see how you did. Now, notice right here when we put our data in, it gives us our scatter plot automatically, right? Does that look linear?
Yeah.
Yeah, so we definitely want to use linear regression. Okay, that almost looks like a perfect straight line, doesn't it? All right, so to get my equation, I'm going to come right here to my scatter plot or regression command, and I'm going to hit that button, and it automatically goes to defaults to linear regression, which it is a linear function, and we can see that our line of best fit aligns perfectly there just about. All right, so our equation is going to be y equals, or we could say y hat, because remember we learned yesterday that y hat means it's a prediction equation, 0.04x plus 1.29. All right, it says, how can we interpret the slope and y-intercept in the context of this problem? All right, so let's look at our slope. Our slope is 0.04, right? And that's the same thing as 0.04 over 1. Slope is the change in your y's over the change in your x's. So for this particular problem, what does the y represent?
What does that say, Miss CP?
Delta y?
No, the equation down here.
Y hat
No, down at the bottom.
equals this right here?
Nope, nope, down where the 9's at.
629.
Right here? 1.29.
See, exactly. Where's this 64?
Okay.
Where'd you get 1.29 from?
from
1.28.
right here.
But there's a 2. Oh.
All right, so what does the y represent in this problem?
It represents the amount of food in cups,
Right, the amount of food in cups. All right, what does the x represent?
the weight of the dog in pounds.
All right, so here, remember I said the statement we're going to write for each additional, and then we put our x value.
Is that for the weight?
Yes. Okay, so for each additional, then we put our weight. I mean, not our weight, we put our x value. All right, and the x value, we put the numerical part of it and the word part of it. What does that represent? So for each additional what? 1 pound of weight. So each additional 1 pound of weight. There will be, all right, so we either got to put an increase or decrease. Since the slope is positive, is it increasing or decreasing? Increasing. So there will be an increase of, and this is where we put our y. All right, so your numerical portion of the y, so 0.04 cups of dog food. So for each additional 1 pound of weight, there will be an increase of 0.04 cups of dog food. All right, so that's our interpretation of slope. Now we've got to do our interpretation of the y-intercept. And remember yesterday we talked about how when you have a y-intercept, every x value is always what? 0. So this y-intercept right here, this is your y-intercept. That would be 0 and 1.29. All right, the x represents your weight, and the y represents your amount of dog food, right? The amount of food. So here, when there is no weight, the dog should be fed how many cups?
There's no weight.
We're going to talk about that. 1.29 cups of food. When there is no weight, when the dog weighs 0 pounds,
But then now add weight.
okay? Because the weight is what? The weight is 0. So when the dog weighs 0 pounds, the dog should be fed 1.29 cups of food. All right, does that sound like it makes sense?
I'm going to trust you, CP. You're the master
Okay.
here.
All right, so let's think of some scenarios where that might make sense.
All right, so the dog got like this.
Okay,
0
so
pounds?
0 pounds.
So it
Dog
might be
eat
like half a pound when it's a puppy,
Yeah,
and
but
it needs to grow. So we don't.
Half a pound.
like Chihuahua.
I mean, like 0.99.
Okay, so in some scenarios, you know, when you have a puppy, they might not be a pound yet, but does it make sense to feed them almost a cup and a half of dog food a day?
Not today.
At a feeding? No. So sometimes we get statements that make no sense, and this is one of those right here. Even if the dog was a puppy that weighed less than a pound, it's not going to eat a cup and a half, almost a cup and a half of dog food. Okay, so
What size cup are they using?
a cup.
Red soda.
Yeah. All right, so again, sometimes we get statements where it doesn't apply. It makes no real world, that has no real world meaning. Okay, so, all right. How many cups of dog food should a dog weighing 240 pounds receive?
None.
Good, man. You don't need to get no food.
All right, so is the weight your X or is it your Y? It's your X. So they're saying when X equals 240. Now there are some breeds, especially your livestock guardian dogs, that are that large, or your Great Danes can be that large.
Are you serious?
Yes. So we're going to come right here. We're going to say x equals 240. And we're going to see where they intersect. Oops.
Blueberries weight.
All right. So how many cups of dog food should they eat at one eat
11.6.
11.6.
He ain't getting 11 points. He might get 5. He ain't getting 11. You gotta cut some weight, buddy. You know, like that.
All right. If the dog is given 10 cups of food, what is the approximate weight? All right. Is the 10 cups your x or is it your y? It's your y. So they're saying when y equals 10, what is your x?
21 and 22.
So we're going to come right here. We're going to change that out to a y equals. So y equals 10. And we're going to look for where they intersect. All right. So approximately 203.6 pounds.
But why are we giving a 19-pound dog 10 cups of food? And a 203.
Remember, this is 190.
Oh.
Remember, I told you that it printed weird?
Oh.
So, yeah. But that's a great observation. If it was 19 pounds, that wouldn't make sense to give them 9 cups of food at one eating, at one mealtime.
21 or 22.
That's some big dogs, man.
All right. So, any questions on how to use Desmos to find your prediction equation or to make predictions?
This is y'all getting $50. I gotta do my homework.
No. All right. So let's come back here and let's talk about some correlations again. All right. Right here, is this a positive correlation or a negative correlation? It's positive. Okay. So I'm going to put a positive right here. All right. This one's what? Negative. What about this one? None. Let's put NA for none. All right. What would this one be? It's rising to the right. Positive. What about this one? That would be negative.
Is that an A/A on the left bottom?
Uh-huh. Is it NA? All right. And then finally this last one, we've got a pattern here, but it's not a linear pattern, is it? So is that going to have a correlation? No. All right. So I want to look at our two positive correlations here. All right. So between these two right here, which pattern is more tight?
The left one.
Right, the left one. So this is what we call a strong positive correlation. The closer the dots are, the points are to each other, the stronger the relationship is between your two variables. This one, you can definitely see it's positive, but it's not as tightly packed as this one. So this is what we call a moderate positive correlation. And then the same is going to apply to these two. If you notice this one right here on the left, that's more tightly packed. So this one's a strong negative correlation. If I can spell correlation right. And this one is a moderate because you can definitely see it's a negative correlation, but it's not as tightly packed as this one. So this is a moderate negative correlation. And remember, negative simply means that as one goes up, the other goes down. It doesn't mean that it's weaker than a positive. It just means it's going, one's going one way and one's going the other. And these last two have no correlation. All right, so the correlation coefficient. And remember, your correlation coefficient has three numbers, -1, a 0, and a 1. The closer it is to a 1, whether it be a negative or a positive, the stronger it is. The closer it is to a 0, the weaker it is. Okay? So we want to see if you can test your knowledge on this right here. All right. So remember the range can be from -1 to 1 with 0 being in the middle. All right. Look right here, this first one. Now remember, this is your R. This is your R value. You also have got an R squared, and we'll talk about the R squared in just a little bit. But the R value tells you how strong the relationship is between your two variables that you're working with.
Ma'am?
All right. -0.8 to -0.5 or +0.5 to a +0.8. All right. So is this closer to 1 or is this closer to 0?
1.
It's closer to 1. So this is because it's not very, very close to 1. This is simply what we just call a moderate relationship. It's moderately positive or moderately negative. Okay. And to visualize this, I'm just going to look at the negative part. All right, here's 0. Here's -1, so here's your -0.5. So it's saying it's between this right here. Okay, so it's closer to a -1 than it is to a 0, right? But it's not exactly in the little range. I shouldn't have done it that far. It's not exactly in the range right there at -1, so it's a moderate strength.
But the other side, the 0.5 and 0.8.
Same thing here. So here would be 1, so point A would be right here. 0.5 is right here. That's closer to 1 than it is to 0, isn't it? Although I didn't draw it correctly, but it is. So it's a moderate strength. On the other hand, like this one right here, here's your 0, here's your -1, here's your 1, -0.5 to +0.5. That's this right here. So that's pretty close to what?
Moderate?
It's pretty close to
Oh,
0. So that's what we call a weak. So anything 0.5 to -0.5 to a +0.5 is a weak strength. That means the relationship between the two variables, there might be a relationship, but it's not exactly the strongest one. Like doing your homework in math versus your grade in English. There might be some kind of relationship you could argue there because, you know, if you do your homework in math, more than likely you're probably doing your homework in other classes. Or if you don't do your homework in math, you might do your homework in other classes. So there could be a relationship that's not exactly the strongest argument. Okay. All right. What about this one right here? These two are the same, just one's a positive version, one's a negative version. So think of it this way. Here's 0, here's -1, here's 0.8. It's talking about right here.
So it's negative?
It's negative for this side. This side will be positive, but is this strong, weak, or moderate?
It's strong.
It's strong because it's pretty darn close to a 1, isn't it?
So you're not determining which side of the or is.
Right, you're just determining how close it is to a 1, be it a negative or a positive 1, or if it's close to 0. You're
So if it's close to a -1 or a +1, it's going to be stronger, and if it's close to the middle, it's going to be weaker.
right. So if it's closer to 0, it's weak.
Are you good, man? Good.
All right. How about if it's a -1 or 1 exactly? It is perfect, yes.
What days do you work?
All right, so now let's talk about R squared. All right, so R tells you how strong the relationship is between the two variables that you're working with. R squared is called the coefficient of determination. And Desmos is going to automatically calculate it for you.
What you mean is perfect?
Okay. It basically represents the percent of data that can be explained by the regression equation. I usually do that on Fridays.
Yes. Don't put it on. What did I say?
All right, coefficient of determination is the percent of data that can be explained by the regression equation. So basically it's telling you how strong your prediction equation is. So if you had something like a 0.24 for your percentage, so that would be 24%, that means only 24% of what the equation predicts might actually happen. So that's a pretty weak equation. But if you had like 0.89, that's saying that 89% of your predictions might actually happen. So the R tells you the strength between the two things that you're working with. R squared tells you the strength of the equation you created from that data. All right, so everybody got this copied? All right, so again, remember that it's easy to get confused when you first see it. R is how strong the relationship is between the two things that you're working with. R squared is how strong the equation is that you made from that data. Okay. So we want to be able to determine how good our data is. There she is. All right. So there's something called residuals that allow us to determine how far off we are. All right, so in reading this right here, we got a scatter plot can be modeled as a linear function using the line of best fit, okay, or linear regression. This line needs to be tested for goodness of fit. If a graph is to be a good predictor of the data, the line must be accurate in predicting the data. This can be found by analyzing residuals. All right, so residuals are error distances. They measure the goodness of fit. To find the residuals of a regression model, you find the difference between the observed value and the models predicted from the equation of regression. So to put it in our words, it's saying, hey, you look at where the actual data fell, you look at your prediction equation, and you find the difference in those values. Okay. All right, so right here, the residual is equal to the actual value minus the predicted value. And I used to say AP, because like AP courses, it's the actual minus the predicted. So, in looking at this scatter plot right here, this is your line of best fit. Okay. The points themselves right here is what actually happened. Your line of best fit are the points that you predicted to happen. Okay, so if this is the actual, and this point right here on the line of best fit is your predicted, you just find the difference between those two, and that difference is your residual. So you're basically trying to figure out how far off you were in your prediction from what actually happened. Okay. Now, a couple of important things that we want to look at right here. All right, especially this right here. A residual is a signed distance. Okay, so you actually do look at the positive and negative version. If you have a positive residual, that indicates that your data point is above the line of best fit. So you predicted low. Because if actually what happened is above what you predicted low, right? A negative residual indicates that the data point is below the line of best fit. So if your actual data is below what you predicted, then you predicted too high. A good line of fit should have about as many points above the line as you do below. So you want to try to have points above the line, same amount below. And you also want to find follow the pattern as well of the data. Okay. And the sum of the residuals of a good line of fit is close to 0. Now, right now, all that probably doesn't make any sense until we actually work out a problem. Okay. All right, we got all that noted. Noted away. All right, so I'm gonna give you a couple of examples on your test next week. It's it's supposed to be kind of an easy test because you know Desmond's gonna do all the work for you, all right?
Okay.
All right, so this is where you need to know your definition. All right, so notice this is not a regular XY axis. All right, this is a residual graph. Okay, it's what we actually call a residual plot. If your residuals have a pattern, it's not a good fit. If they are close to your x-axis, then it is a good fit. So are these close to your x-axis? No. So this is not a good fit, which means your prediction equation is not that strong because you're predicting all over the place from what actually happens. All right, look at example 2. Again, this is a residual plot. Is this close to the x-axis? Yes, so this is a good fit, which means your prediction equation is giving you predictions that are pretty darn close to what actually happened. All right, so here comes the hard part. Putting the data in. All right, so we're going to come in here, we're going to put this data in. So go to Desmos, and let's put this in X and put this in Y. All right, does everybody get your data in? All right, so as you're finishing up, notice that it labels this one as x of 1, this one as y of 1, right? This right here, what they give us is what actually happened, but we need the predicted values. All right, so this is something new that you have not seen before. You see what y sub 1 is? Click right there to the right of y sub 1. There's another column there.
Wow.
We're going to put in 8.7 x sub 1 plus 58.6. Okay. Here are the predicted values. So let's write those predicted values right here. Now the reason why we had to call it x of 1 because that's how the calculator is going to recognize it because it called this column x of 1, y sub 1. All right, so you simply just come in there. You got 8.7, you got an X. Now just hit a 1. And it automatically gives it to you. All right, so The residuals, remember, are the difference between what actually happened and what you predicted to happen. So these are the predicted values. All right, we want to find the residuals. So again, we're going to let Desmos do the work for us. So go to the fourth column and click right there. All right, we want the actual values minus the predicted values, right? All right, what's the actual values called in Desmos? Y1. So we're going to type in Y1. Then we're going to say minus. I'm going to do parentheses, and I'm going to put this equation right here back in. So 8.7 x of 1 plus 58.6. And it's automatically subtracting these two right here for us. So the difference between 63 and 62.95 is a positive 0.05.
You said positive?
Positive, yep. Alright, so there's our residuals. So we're not too far off from what actually happened, are we, with our predictions? Alright, so we're going to come over here, we're going to do a residual plot. Now I notice here that the residuals don't go beyond a 1. So I'm going to, when I do my x values, I'm going to keep that in mind. Right here, my actual x's let's do 0.5, a 1, 1.5.
I can't see the line.
Just write it in. 2, 2.5, 3, and 3.5. All right, and here, really the biggest number I've got is 0.05, so I'm just going to go to a 1 and a 0.05 for my residuals. And right here, a negative 0.05 and a negative 1. All right, then I'm going to start plotting. At 0.5, my residual was 0.5. Actually 0.05, so that's pretty darn close to 0. At 1, it's negative 0.3. So here's 1, negative 0.3. I meant to do that as a 5. That's 0.5, not 0.05. Alright, I meant to do a 0.5 there, not a 0.05. So 0.5 and negative 0.5. Alright, so let's see. At 1 is a negative 0.3, so it's going to be right about here. At 1.5, it's positive 0.35. At 2, it's exactly 0. At 2.5, it's negative 3.5. At 3, it's 0.3. And at 3.5, it's negative 0.05. All right. Are they pretty close to the x-axis? Yes. There's no pattern. They're all grouped around their x-axis. So would this line, regression line, be a good predictor of the equation?
Yeah.
Yes. And then right here it says, what do all the residuals add up to? Well, right here we got a positive 0.5 and a negative 0.05. So they do what to each other? Negative 0.3, positive 0.3. They cancel. Positive 0.35, negative 0.35. So they cancel. So what does everything add up to be? 0. So that lets you know this is a pretty good indicator that your prediction equation is a strong prediction equation. All right, so does everybody kind of see how to do residuals? Okay. Again, the calculator does all the work for you, so that makes it pretty nice. All right. And that's it for the notes. Woohoo.